Hello everyone, today I'm going to present a very quick guide on how to use an open source code for finite element analysis called MoFEM. I assume that you have installed MoFEM and you are familiar with basic Linux command, and if not, look at the useful links in the description. So we will start with going into executable directory in our MoFEM installation. So typically MoFEM installation is in our home directory, as we see MoFEM install. Next we want to go to user modules. Sometimes there's additional folder called build. In that case I don't have this, so I can jump directly to the basic finite element and elasticity, and this is our module, and this is the place from which we are going to run our calculations. So first things first, we need to generate the mesh, and for that we are going to use software called Cubit. If we are on Linux, you can just type Cubit and ampersand to start up Cubit in that folder, and on Mac I have this already open, so we can start generating our mesh. To start our workflow for generating mesh, the best thing to do is to open journal. What this thing does is basically keeps our journal of the commands that we are using to create the mesh. Usually in the user modules, in the documentation of user modules, we can already find some example and prepared journal files that will generate some basic meshes for the problem. So we will start simply with typing reset. So what we'll do is that every time we run this journal file, it will reset our workflow, and we will have our new freshly created mesh. So we're going to keep it on the side, and the first thing we want to do is to generate some basic entities. So we will create a simple brick like so with the dimensions 115. As you can see, it looks like this, and it created our journal command brick, so we can copy that and then go to our journal file and save it for later. And now you see, if we play this journal, it will do exactly it will repeat those commands. Next thing we could do is to generate another brick, for instance with dimensions like this, right? So it will create another volume which is inside this one, and there's lots of tools in Cubit, and one of them, for instance, is Boolean operator. So we want to subtract volume 2 that we just generated from volume 1, and that result in this nice bar with the hole. So this is going to be our basic geometry that I'm going to use. So in the next step, what we can do is to generate boundary conditions. So for that we click here and we will create some basic displacement boundary conditions. So we clicked here, we're going to select this surface and then click select that we are going to fix all those degrees of freedom here. Don't forget to copy your commands. even put a comment and restart and see if it's all working. Yes, we have our body with boundary condition. Next, we can create another boundary condition from the list, and it's going to be force. We will choose it on the surface, for instance surface number 17, and we're going to choose that for force is going to be value. We're going to have a value of 1, and direction, let's say direction Y, and apply. So that generated our force. We can paste it right here. Okay, so we have our basic boundary conditions. The next thing what we could define is material properties. This is very specific based on the which user modules, which user module you are using for MoFEM. But in case of elastic materials, what we need to do is just to define a block for the volume. Let's say select the volume 1, apply. So we created a block that contains our entire volume like this. Next thing what we want to do is select this block here from the tree, and we want to change its name to Mat Elastic, and we can call it Mat Elastic 2, 3, it doesn't matter. It's because we can have many materials, but it's important to have Mat Elastic. So in that way we are telling our MoFEM that this is elastic material. And again, don't forget to copy this command into the journal. In the next step, we want to define two attributes for this block. So we set that the attributes count is 2, and in terms of material elastic, first one is going to be our Young's modulus. So let's say we set the value of 1000, and the second one is going to be our Poisson ratio. So in that case, let's just choose it to be 0.1. So we have our material properties defined. They are very basic. So the next thing we can do is to discretize our geometry. So we click on the meshing module, which is the volume mesh. Okay. And the first thing we want to choose is to meshing scheme. So let's say we have just one volume, so we can click that we want to select the volume 1, or if we have more, it would be easier if we just type all, right? And currently in MoFEM we have only tet mesh, so we are choosing the type to be tet mesh, and apply scheme. Next, we can choose the size of our mesh. Let's just choose to be automatic, and that we're going to have relatively coarse mesh. So apply. So there we go. This is our basic first tetrahedral mesh of our bar with a hole. Don't forget to copy the command again, mesh volume. Okay, so the model is ready. The only thing now we can have left is just to save file, right? So for that we just use here, and we can choose the location where to save our file. So I will save in the user modules, basic finite elements, and Elasticity module, and I will call it bar with whole cube. This is our cube file. Okay. Also, don't forget to save somewhere our journal file. This command here is going to be useful. Okay, so we can also save somewhere our journal file. This is simple text, but you can also and now finally we are going to run the analysis. We are going to finally solve a simple elastic problem in our elasticity module. So as you remember, we are in the executable directory of the elasticity. So in order to run the calculations, we need to type mpi run np2, which means we are going to use two processors. If we have more, then we can type 4 or 8 or even 30 if it's on a server. If we want to use just one, we just type 1 or not write it at all. Okay. Next thing is our executable elasticity. Then our next parameter is my file, in which we are pointing which mesh file we would like to use. So as you remember, we want to use our bar with the hole. All right. Next thing we want to define is my order, which tells us which order of approximation we are going to use for our tetrahedrons. So we will start with order 1, and the next thing we need in that case is just to write what is the type of preconditioner. This is usually not necessary, or we can find in the documentation of the of our used user module what are the necessary parameters in order to run analysis. So we can press enter, and our problem is already solved. We can see the resulting elastic energy. So now what program did is produce an output file, out.h5m, like this. What we need to do right now for processing, we need to convert that file using the command of mbconvert out h5m to out.vtk. And now we have a VTK file which we can open in the Paraview post-processing software. Now we can open Paraview if it's on Linux, then by just typing Paraview and ampersand. On Mac, I will just click on the icon. And open the output file that we just generated. Okay, so this is our mesh with the results. We can see the displacements. We can see stresses. For example, the mesh is very coarse, so that's why they look like that. In order to present the formation, we can click here, and it will warp by vector automatically by vector of the displacements. So we can change here and show the displacements We can also increase the multiplier, for instance 5, and now we see our displacements multiply 5 times. The last thing I would like to show is how to run H and P adaptivity. So in case of P adaptivity, it's very simple. In MoFEM, we can increase the order of our approximation by just changing this parameter here. And as you can see, we have analysis for the second order, for the third order, and as you can notice from the elastic energy, it's slightly changing the values. They should be converging to the exact solution. So again, we can convert. Again, open this file in the Paraview. Just again, this is our new results. Again, as you can see. Now, we don't see much improvement on the displacements, but stresses are now second order, and now you can see the approximation looks much better. We can even run fourth order approximation. It's going to look like this. As you see, calculations now take even a bit longer. Again, MB convert, and we can open the file again. Right. In that case, stresses still look almost the same, because it's hard to observe fourth order polynomial approximated on just one tetrahedron. But what we can do is to use a MoFEM feature called post-processing refinement. So we can use the parameter my max post-process ref level, for instance 3. So what it will do is divide our mesh in a way that we can observe the increasing order of approximation. So again, convert. And again, open file. As you can see, the mesh is much denser, but this is only post-processing mesh, and here's how we can observe our stresses are even more smooth. Okay, the last thing I would like to show you is simply how to run H adaptivity. So for that, we can just go back in our MoFEM. As you remember, we have this drawn to Cubit. As we remember, we have this journal file, which is looks like the following instruction, right? And it generates our mesh. So what we can do here is simply change the size factor to 5, run the mesh again, and this should now run our much more refined mesh, as you can see. Okay, so this is already saving the mesh, actually overwriting. So what we can run again, let's say with lower order, and the last thing that we can do is open our mesh with the P, with the H refinement, as you can see. Very useful thing to do at this point would be to run H versus P adaptivity refinement, and look, for instance, how the values of elastic energy are changing, or maximum stresses or displacements. Okay, so that will be it. Let me know in the comments if you have any questions. You can also post questions in our MoFEM group. A link to the website you will find below, and I hope that was useful. Thank you.